All right. Hi, everyone. Welcome to ML Observability Journey at DoorDash, and thank you for attending this session. Nachiket and I will be the presenter of this session. Here's our agenda. First, I will provide a quick overview about DoorDash and our ML use cases. After that, Nachiket will present our approach to ML observability. And finally, he will end the presentation with a few lessons learned and future work. Before we get going, here's a little bit about us, starting with me. Currently, I'm leading the ML platform team at DoorDash. Before that, I work at LinkedIn as well as at Uber.
Hi, everyone. My name is Nachiket. Currently, I'm working as a software engineer on the machine learning platform team. Previously, I worked at a startup called Formation in San Francisco. Back to you, Hien.
Cool. So at DoorDash, our mission is to grow and empower local economies. And we do that through a set of product offerings. First, food delivery and pickup, where customers like you and me can order food on demand for breakfast, lunch, or dinner. Second, we have convenience and grocery, where customers can order everything from non-food items, such as sunscreen, to an entire week's of groceries. The last one is called Dash Pass, which is a subscription product that is similar to Amazon Prime. You probably can guess, I have heard that DoorDash is a three-sided marketplace. And like most of these marketplaces, it has this flywheel effect, meaning the more activities there are on a marketplace, the greater the value it will bring to all parties. I will share our ML use cases through the food ordering process. So let's start with the order creation step. When customers land on a DoorDash homepage, we want to surface the most compelling options to them. And this is where our recommendation models play a big role. And if customers don't see something they would like on the homepage and decide to search, this is where we leverage a set of search and ranking models to help with providing relevant search results. Once the food items have been added to the shopping cart, the next step is the order checkout. The left picture shows the ETAs, meaning the estimated arrival times, which are really important for setting customer expectations on when the food is going to arrive. Therefore, it is critical to have accurate ETAs, which are predicted based on a number of factors, including the size of a shopping cart, the historical store operations, as well as the number of dashers available at that point in time. So we have a number of ML models for predicting ETAs. The right picture shows the payment section. And like most internet e-commerce companies, we need to combat fraud. So we use a series of fraud detection models to identify fraudulent transactions. Once the order has been paid, then the next step is to dispatch that order. This is where our core logistic engine takes over to send the orders to merchants and assign orders to dashers. And in order to do this effectively and efficiently, it relies on several ML models, such as predicting food preparation time, like how long does it take, and also predicting the travel time, which has a few interesting nuances, such as traffic, weather, where we don't have much control of. One interesting challenge in this particular area is, unlike Amazon orders, food orders emerge on the fly, and the food quality plays an important role in the delivery. Finally, the last step is to deliver the food to the customer's doorstep. The ML use cases in this step includes routing, image classifications, and more. During the pandemic, we introduced the contactless delivery. So we asked dashers to drop off the food near the front door and take a photo of the food, and then send it to customers as well as to DoorDash. And this is to help customers finding their food easily. We use deep learning models to identify whether the drop-off photo is valid or not. And now I'll hand over to Nachiket to talk about our ML observability journey.
Hey, thanks, Hien, for walking us through all the different ML use cases at DoorDash. So as we grew the number of use cases, ML use cases at DoorDash, we realized the need for having monitoring around the same. Today, I would like to share a bit about how DoorDash integrated monitoring into its ML platform. Once we integrated machine learning systems with our product, we saw that there was a need for monitoring. data scientists wanted to know what decisions were taken and why. We then consulted with our data science teams to understand what would be the most helpful for them. And based on that feedback, we quickly implemented a first version of our monitoring, trying our best to adhere to MLOps principles. We immediately saw the benefits of monitoring, and we ended up iterating on it to get more out of it. So why observability? ML gives us reliable signals for the time it takes for a restaurant to prepare a food or how long it takes for an order to reach a consumer. However, once an ML model is deployed to production, it's susceptible to degradation. This degradation negatively impacts the accuracy of our time estimates. Model predictions tend to deviate from the expected distribution over time. For example, a shift could be the result of an external event, such as the COVID-19 pandemic that we saw, caused a huge shift in how the customers interacted with DoorDash. Using observability and monitoring, we wanted to protect the downside and avoid bad outcomes. In a few cases where we went through a migration to a new feature upload system, for example, and experienced some issues in our downstream model prediction services. Had we had monitoring at that time, we would have been able to detect these shifts sooner and fix our models. And as we built out more mature systems, we realized a need to have systemic performance monitoring as well. We have also uncovered several other issues with things such as feature uploading from feature defaulting alerts that we have set up. So what needs to be monitored in a machine learning system? Because ML models are derived from data patterns, their inputs and outputs need to be closely monitored in order to diagnose and prevent model drift and feature drift. We believe that monitoring and testing should be present in every step of the way, but we are focusing on these major areas: data quality, model training, prediction, and general system performance. Additionally, our users also like to understand why a model made some specific predictions, which we refer to as ad hoc inquiries. In this table, we have laid out a high-level view and added the areas into two dimensions: observability and explainability. For data quality, we are investing into a data quality service, which includes adding safeguards to data inputs before they reach the training phase. For training, prediction, and system areas, we've developed some in-house tools and also use industry standards such as Shapley plots for helping users understand these areas. Finally, we power ad hoc inquiries by providing dashboards and notebooks, as well as a one-stop ML portal UI, where data scientists can now have an overview of their ML applications and the system. Today, we will cover model training, model prediction, and system performance in more detail. Before I dive into these areas, I'd like to talk about some of the strategies, or one of the strategies that we have incorporated. In order to make ML observability setup easier for implementation and adoption, we tried our best to leverage existing tools and technologies that we use at DoorDash. For example, we already have data pipelines set up, which ingest data with Snowflake and have used Databricks for compute. By using Slack and PagerDuty to notify our users for issues with their models, we saw that the users were also comfortable adopting this new monitoring setup for their models. Now let's take a look at model training. During model training, we want to make sure that the inputs that we feed into the model are as expected. We verify that there are not excessive amounts of things such as missing values, and the distributions of features are also as expected. We also want to track our training runs, and open source tools such as MLflow have been extensively used by us and have been extremely helpful in uncovering observability for model training. While setting up training instances, data scientists look at various properties of features such as distributions, percent of negatives, missing values. Here's another example of how that looks internally. We use some internal build tools to achieve these reports on the quality of data in the training instances. Another standard way of looking at the effect of features on the output is a game theoretic approach called Shapley. This is another model observability tool used by data scientists, and we create various plots similar to this one. Data scientists can access these through our ML portal UI. We have also recently enabled the SML folks to view feature importance plots for tree-based models. This is another visibility tool that we have exposed through our ML portal UI. Next, let's take a look at the model prediction side of things. In our production environment, when we receive a prediction, we log it along with the features and the prediction value to a Snowflake table. Having all our predictions logged in a structured way allows us to construct queries against these tables to derive statistics such as averages or percentiles. We can also set up compute jobs to extract this information from these Snowflake tables and stats at a regular cadence. This has allowed us to take a look at the historical performance of our features as well as our prediction scores. Once a prediction is logged, we also want to monitor the outputs of these ML models and the predictions. We monitor descriptive statistics for model predictions. Model AUC curve is another such statistic that we monitor. For example, we predict the expected time it takes to deliver an order, as Hien explained previously. And we want to monitor those predicted values over time. We want to make sure that there are no unexpected outliers in order to continuously provide a great user experience for DoorDash customers. Now I'll talk briefly about the feature quality monitoring setup. We launched Fabricator, a declarative way for creating features in Q4 2021. And that has enabled our users to create new feature pipelines at a very fast pace. Features by nature undergo some degradation in time, and hence we realize a need to monitor this feature drift over time. Feature storage also has costs associated with it, and it can get expensive. And in order to avoid feature storage costs on unused features, it is often important to monitor this feature drift. Feature quality monitoring initially started with us setting up Flink-based real-time jobs to track the prediction events which go to the Snowflake tables. We found that this was not only cost inefficient, but also difficult to scale. After an iterative process of trying to improve this setup and talking to the data scientists, we decided to take a two-step approach for setting up monitoring on the feature quality. We noticed that the defaulting features had the most adverse impacts on our models, and hence feature defaulting had to be alerted most immediately. Similarly, stats such as mean, standard deviation, average values, percentiles, although important, can be notified and monitored at a lower cadence. We hence came up with a two-tier approach of high-tier or critical alerts, where we monitor defaulting features, and low-tier or info alerts, where we monitor other stats. Another thing to note here is that we went with an opt-in approach for low-tier alerts, where data scientists, users could now set up low-tier monitoring for different features to monitor their performance. We publish all our metrics to Chronosphere, and by setting thresholds, users can now get notified directly for any misbehaving features. So here's a look at a sample YAML spec for an info alert. Our main theme in setting up feature quality monitoring was to make it self-serve. We allow users to define YAML files like this to set up monitoring for low-tier metrics such as percentiles, mean, standard deviation. We also wanted to make it as easy as possible for a user to set up their own monitors. As we see in this example above, we have now created a monitor which will track P99, P95 mean, as well as a standard deviation for features A, B, and C for the given model ID. This is a simple YAML file, which when added to our repo will create a monitor which sends out metric data to Chronosphere, where they can now view their metrics. Similarly, for high tier or critical alerts with more strict SLAs, we chose to set up these via simple Terraform templates. High tier stats or default stats, as I explained previously, are logged to Chronosphere by using real-time Flink application pipeline. Users can now add a template as seen above, where they can define the model ID, the threshold, and the features they want to avoid tracking to set up a feature defaulting alert. Next, I'd like to talk a bit about system performance. As we went ahead in our journey of setting up model observability, a lot of data that was to be monitored comes from systems and services on the ML platform. It was hence equally important to monitor the health of these systems to ensure reliability of the ML observability setup. We follow standard service reliability best practices and monitor requests, prediction counts, availability, and latency. We have tight alerting on each of these components, since other systems such as the delivery team, the ETA team, and the fraud rely on our prediction values. Changes in quality can have significant impact on these sister teams as well. Next, let's take a look at the takeaways. Along the way, we saw a few benefits of developing our own production monitoring systems. The first one, as I mentioned previously, was to leverage existing tools. We can design a configurable and flexible platform for displaying metrics and setting up alerts by reusing these tools. And as mentioned earlier, this has helped us with development as well as adoption of ML observability at DoorDash. The second is no onboarding should be required, which means that the data scientists don't need to individually write code to add monitoring to their training pipelines. They only need to add configuration files if necessary in some case, but otherwise none. They also do not have to think about the scalability and the reliability of the monitoring solution. The next one is easy visualization. Graphing tools such as Chronosphere offer the ability to interactively view and split historical data. This is an incredibly useful tool when it comes to finding correlations between events. And finally, self-serve. Data scientists can use this tool without the help of the platform team, which enables us to have a more scalable solution for detecting model and feature drift going forward. Finally, lessons learned. Firstly, scaling out doesn't always work. Sometimes you have to think outside the box or get back to the drawing board. And as we all know, scaling comes at a cost associated with it. The next is opt-in versus opt-out. Opt-in and opt-out can both work in different use cases. For example, for all the models in productions, we have by default default enabled model monitoring metrics. However, for feature monitoring, we currently have gone ahead with an opt-in approach. Providing an out-of-the-box solution is preferable in most cases. Automation is key for any large-scale system. And if you have good foundational tools, you should use them. By enabling an opt-in approach, we saw a lot of reduction in noise as well. The next is that we've learned that using existing tools can be very beneficial. And finally, and most importantly, I'd say, working closely with our customers is necessary for a good outcome. We have seen that in having a constant feedback loop with our customers who are data scientists has helped us identify several edge cases and helped us build a data scientist-friendly ML observability solution at DoorDash. So that's it, everyone. Thank you so much for attending this talk. And if you have any other questions, feel free to let us know. Thank you.